Welcome to error bounds of Taylor approximations. So recall Taylor's theorem gave us a bound for the error of P sub n, our nth Taylor polynomial, in approximating f. Over interval I containing C. And what that bound was that the difference between f of x and P sub n of x, the absolute value of that difference, is less than or equal to the maximum of the absolute value of the n plus first derivative of f evaluated at z, all divided by n plus 1 factorial, times the absolute value of x, not z, of x minus c raised to the n plus first power. So let's go ahead and consider the function f of x equals sine of x. Our job is to find an error bound when approximating sine of 2 with the Taylor polynomial of degree 5 of f at x equals pi over 2. In other words, with the 5th degree Taylor polynomial of f at x equals 2. So I'm going to change this to with the 5th degree so that it's not quite so awkwardly stated. Taylor polynomial of f at x equals pi over 2. And then after that, we have our job is to figure out which degree Taylor polynomial is needed to approximate sine of 2 to within 0.0001, so to within 1/10,000th. So in this case, we have our f of x. We are trying to approximate the error at 2. Oh, I should specify we're looking at x equals pi over 2, so our c is pi over 2. And we want to approximate or to find the error bound on absolute value of f of 2 minus P sub 5 of 2. Right? That's what we are trying to approximate our error bound on. So we have our formula, right? We need to know essentially the max of our n plus first derivative over some interval containing both pi over 2 and 2. So what do we need? So we need max of the absolute value of the n plus first derivative of f of z. And this is over some interval containing both pi over 2 and 2. So we know f of x is sine of x, we know what its derivatives look like. So note, since f of x equals sine of x, then for any derivative, for any n or n plus 1, for any n, the n plus first derivative of x, if we take the absolute value, is either absolute value of sine of x or absolute value of cosine of x. Right? The cosine sine derivatives kind of cycle through sine cosine with some positives and negatives involved. But if we take absolute value, we can ignore those positives and negatives and just do absolute value. We know even over any interval, sine and cosine absolute value are both bounded by 1. So we know that over any interval, absolute value of sine x is going to be less than or equal to 1. Absolute value of cosine x is going to be less than or equal to 1. So what we get is that the absolute value of the n plus first derivative of x must be less than or equal to 1, just in general, right? So we can put that back here. If we want to find the max of that function, well, the max is no larger than 1 on any interval, right? So what we get then is that the max of the absolute value of the n plus first derivative of z, right, is going to be less than or equal to 1. And so since we're just trying to do a less than or equal to, we can just bump that up to 1. So we have that the difference between f of f of 2 minus and piece of n of 2. We have that this has to be less than or equal to the max of, again, that absolute value of n plus 1 derivative of f over n plus 1 factorial times our, where's our original formula, times 2 minus pi over 2 raised to the n plus 1. So times 2 minus pi over 2 raised to the n plus 1. This is true for any n. So for, we had x equals 2, pi over, c equaling pi over 2. This is going to be less than or equal to, that max is just, has to be less than or equal to 1. And then we have over n plus 1 factorial times absolute value of 2 minus pi over 2 raised to the n plus 1. We wanted to focus on n equaling 5. So now plugging in n equals 5, we are looking at the absolute value of f of 2 minus p sub 5 of 2 is less than or equal to 1 over 5 plus 1 factorial times the absolute value of 2 minus pi over 2 raised to the 5 plus 1. So we are looking at 1 over 6 factorial times 2 minus pi over 2 raised to the 6th as our upper error bound. And if we go ahead and plug that into a calculator, we have, let's see, 1 divided by 6 factorial. And then times 2 minus pi over 2 raised to the 6th. And we get that our error bound is 8.683 times 10 to the negative 6th, or in other words, that error is less than or equal to 0.00000086 ... So this is a very small error for estimating sine of 2, right? So this means that piece of 5 of 2 is almost identical, is essentially sine of 2. Right? Now the question is, the next question was which degree Taylor polynomial is needed to approximate sine of 2 to within 0.0001. So next up, we wanted to know how large of n is needed to approximate sine of 2 to within 0.0001. So we've seen that n equals 5 does the trick. The question is, could we use n equals 4 instead, right? So we've seen n equals 5 works, right? Could we have used a smaller degree instead? So if we look back at our work, we had an error bound that was just in terms of our general n, right? We saw that f of 2 minus p sub n of 2, absolute value of that, was less than or equal to 1 over n plus 1 factorial times the absolute value of 2 minus pi over 2 to the n plus 1. So earlier, we saw that the absolute value of f of 2 minus p sub n of 2 was less than or equal to 1 over n plus 1 factorial times the absolute value of 2 minus pi over 2 raised to the n plus 1. So what we do here is we want, let me do this in another color. So we want this to be less than or equal to 0.0001. So In this case, it's definitely not something that's easy to solve for n. We just do guess and check until we find the smallest n that satisfies this. So what we do is we just, again, do guess and check. Until we find the smallest n to satisfy the inequality. So to satisfy 1 over n plus 1 factorial times absolute value of 2 minus pi over 2 raised to the n plus 1 is less than or equal to 0.0001. So if we plug in n equals 4, we have 1 over 5 factorial times the absolute value of 2 minus pi over 2 raised to the 5th power. It turns out that that is equal to 1.213 going on times 10 to the negative 4. So this is 0.00012 ... That's too large. Right? N equals 5 works, as we saw. And so piece of 5 of x, which would be the sum from n equals 0 to 5 of the nth derivative evaluated at pi over 2 over n plus 1 factorial. Sorry, over n factorial times x minus pi over 2 raised to the nth approximates sine of 2 to within so approximates sine of 2 to within 0.0001. And in fact, it did better than that. Note f of pi over 2 is sine of pi over 2, which is 1. F prime of pi over 2 is cosine of pi over 2, is 0. The second derivative, pi over 2, is negative sine of pi over 2, which is negative 1. The third derivative is negative cosine of pi over 2, which is 0. The fourth derivative is a positive sine, which is 1. And the fifth derivative is a positive cosine of pi over 2, which is 0. So in this particular case, it winds up that the fourth and fifth degree polynomials are the same. So we actually could have used the fourth polynomial. It's just that our error bound was generous. So this means that piece of 4 and piece of 5 are the same. So P sub 4 actually works. And our bound was generous, right? So when we do our bounds, again, on the derivatives where we're on cosine, pi over 2 is 0, or cosine of pi over 2 is 0. So near cosine pi over 2, near cosine of 2, right, you're going to be much smaller than 1 as your bound, essentially. But so just things to keep in mind for our bounds, we can always be generous. We don't have to get the most precise bound possible. So if you have cosine signs involved, you're welcome to always use that trick that in absolute value, they're bounded by 1, right? You don't have to get the most precise bound possible. So that is how we can go about finding our bounds and or finding the n needed to get the size bound that we desire.